discuss two approaches. One is based on a pure text machine learning based, classic traditional machine learning based approach, and one based on LSTM. And we'll see how LSTM model can be used for this purpose. So that is the approach that we are going to discuss today. So let's start with very basic, I can say a classic NLP pipeline, how we can implement for text classification. So basically what is text classification? Any classification is a supervised learning task. So that we'll discuss. Again, I will note down the points. I have no specific slides for this presentation. So text classification is a supervised learning process. Supervised learning means we have a set of label data is there. Based on the label data, we train a model. The model will learn the labels, and based on this learning, it will predict the data, predict a new test data. When a new data comes, it will make the prediction. So that is generally a classification. In this classification, supervised learning, this classification, the label is discrete data. That means a set of discrete labels. For example, image classification. Images have labels. Say these are the images of dogs and these are the images of cats. We train a model with this set of images, this set of labeled images, and when a new image came, the system is expected to make prediction whether it is yes or no, or color prediction, spam or not spam prediction. So there are many applications. This classification have many applications. A counterpart is regression, a supervised learning, again supervised learning method. Label data is there, but in this case label will be a continuous data, like stock market value prediction, weather prediction, temperature prediction, mark prediction, average rating prediction. So in all these cases we are predicting a continuous value. So that case is called regression. And classification, we are making prediction a discrete value, a discrete label of the output. And text classification, again the input is text, and we are making prediction or prediction of the labels for this text. So there are plenty of application of text classification. For example, email spam classification. So email is spam as text document. So this document need to be represented as either we need to predict it as whether it is text spam or not. Based on the text property, based on the content in the email, can we define the email as spam or not spam. It's a binary classification problem. Or sentiment analysis. Sentiment analysis in the sense a text document is there, text review is there. Based on this review, we need to predict whether the sentiment of the review is positive or negative. For example, Amazon prediction, Amazon's product reviews are available, customer reviews are available as a text document. From this text document, can we predict whether it is a positive review or a negative review? A similar thing is ham or non-ham message. So social media tweets, posts are very frequent. Can we predict this tweet as harmful or not harmful, or normal, neutral? So can we check the polarity, whether it is positive polarity, neutral or non-neutral? So all these are example of text classification. What we discussed is very binary classification. It can be multi-class classification. For example, news article classification. A news article can be classified into, say, politics, science fiction, or some local politics. In that way, we can divide the article into main category. So a news desk can automatically categorize this incoming news into different categories. So in that case, it becomes a multi-class classification. Multi-class means in the previous examples on the output label is only two labels, binary 0 or 1, spam or not, positive or negative. So only two class binary classification. But the other example like news news categorization, author identification, gender identification from the text, gender identification now so that questions no, author identification, news categorization, everything is now multi-class classification. So based on the problem, we can have either binary classification or multi-class classification. Now, text classification, how we can start. So we'll take a simple approach for text classification. We need a data set. So based on the data set, we can, like whatever be the data, we can uh, do the classification. So the text mining approach, so for any classification, any machine learning process, the steps or the pipeline, generally called the pipeline, is like this. We start with loading the data. We need to collect the data and load the data set into our program. Then we need to do some kind of EDA or some pre-processing. EDA to understand the data. Only by understanding the data only we can do the process. So an EDA is recommended. We are not going to discuss EDA, but it is optional. Exploratory data analysis is optional but highly recommended, because we need to understand the data. Based on the data property only we can decide the solution. So an exploratory data analysis. Then we'll do the pre-processing. We'll discuss the pre-processing steps in detail. Then we'll select a model. Select a model. Train the model. Test and evaluate, and based on the evaluation we can fine tune the model again. Like if evaluation, if accuracy or the precision of the model is not good, we can even compare, we can even fine tune the model to get better results. So these are general steps involved in any text processing problem in classification. So in training means we are selecting a classification model. Here it is classification, text classification. So we'll select a classification model. So we'll discuss two approaches. One using a simple text classification using some traditional machine learning algorithm like logistic regression or k-nearest neighbor algorithm, decision tree, such kind of machine learning approach, where we have to work on the feature part. And second one is based on the deep learning model, LSTM model. So this is our approach. We'll discuss two approaches. One is traditional machine learning. So load the data, load the packages. It is common for everything. Any problem, we need to load the necessary data. So here we need some packages like pandas. For the data set is normally in the form of CSV data. So we'll use pandas to process this CSV file, and it involves many metrics array operations. So NumPy can be used to that process. So pandas, NumPy, and this beautiful soup is a package that can be used to clean the text. We can clean the text by removing the HTML tags, unwanted punctuations. Everything can be done using this package, and regular expression may be required. NLTK stop words can be incorporated. Then count vectorizer DFID vector, because we need to convert the text document. We need to learn a representation from the text. So how to represent the document? That is a question. So for that purpose, we can use count vectorizer and DFID vectorizer. And we will import some packages, classification algorithm, which can be used to perform the classification. Any classification algorithm we can use: random forest, logistic regression, linear regression, or k-nearest neighbor classifier, metrics, anything can be used, and we need evaluation metrics to evaluate the performance. So these are the classification packages that we are going to use. We are not implementing any model. We are just using the scikit-learn model, scikit-learn implementation of the scikit-learn implementation of the classifier, just to experiment. We are not implementing. Our objective is not to implement the model. We are just using this model. We are applying this model on our text data. Okay. So we are using a trained label test. This is an example. This is basically a movie review data set from IMDb, and we'll classify the text as positive text or negative text. So basically, it is a kind of sentiment analysis, a text classification, a version of text classification, which is sentiment analysis, where our objective is to identify whether it is positive or negative, whether the class is positive or negative. So that is our prediction, our model. So we first load the data So here is the file name. So we can use the pandas library to load the data. So we are using pandas dot read CSV. It's a CSV file. Even though it is CSV means comma separated file, it is TSV file. So instead of comma, the documents are separated by tab. So we can specify this function read.csv, this file, which is separated by tabs, and we'll read the data. We'll read the data. So this is the first review. You can see the first review. So IMDb data set is actually web scroll data. So all the reviewers write their review. So they are in a HTML format. So you can see some kind of HTML tags here. I have BR. So this kind of tags may be there inside this review. So the first step in this processing is pre-processing. That means we need to we need to clean the text by removing all these unwanted tags. Okay, so for this purpose, we can use a package called Beautiful Soup. So we'll use Beautiful Soup and we'll take the review, this review, every review, and apply on the Beautiful Soup, and we'll get the text, which remove all the tags. So you can see the difference here. Before applying the cleaning, this contain many tags like this. So after removing, it is now all the tags are removed. So it is now ready. Okay. Then we can also apply some more pre-processing. There may be some unwanted characters, some punctuations may be there. We know that we are reviewing the text content, so we can use some regular expression to remove letters and unwanted characters, question mark, or some codes, numbers. So these are not required. We are focusing only on the text content. So only characters, letters are required. So we can use a regular expression. We defined a regular expression. So in Python, a module RE is there, regular expression. So what we are doing is we are substituting all other characters other than the letters with a space or null, nothing. So this simple represent other than A to Z and A to Z. A to Z is very explicit. A to Z means all the character between A to Z alphabets and capital A sets. So everything other than this capital A set to our lowercase alphabets will be replaced, substituted by a space or a null, not a space and a null value. So we can see that here we have something like this. Some codes are there, some question marks, some punctuations are there. So everything is replaced by a space. So everything is replaced. Then the next question is case. We are doing some pre-processing on the text. So these are the pre-processing stage. We first removed all the unwanted tags, web tag. Then we removed the other than characters, non-letter characters. So everything is removed. Now we are thinking about say this capital width is there, small width may be there, some characters in uppercase, some same word may be in lowercase. So for example, the in capital letter is there, the in small letter may be also there. So do we need to consider do we need to keep distinction between this capital the and small the, or capital with capital letters, and some but is like this, some but sometimes but is represented by UT. So do we need to keep distinction? So for the purpose, we are not distincting between those capital letters. We are ignoring the case. So what we can do is we can apply dot lower function, which convert everything into lowercase, and we can use a space as a split to split the data. So we will get all the words which are in lowercase, because everything should be uniform. Then if we want, we can use stemming, lemmatization, everything, stop word removal, everything we can use. So now we have all the words which are in lowercase. So every words are in the same case. We can apply stop word removal. So all the stop words are removed. So yesterday we discussed the stop words. So we can use the same code to remove the stop words. If it is not in the stop word, we'll keep the word. And finally we'll get the words. So these are the list of words with respect to the first review. So we are processing only one review. So All the steps, just remember, we just removed the tag, then removed the all other non-alphabet characters, then we converted into lowercase, and we removed the stop words. So all the steps we can write it as a function, because we need to apply it on all the document. We just applied on the first review, so this should be repeated for all the reviews. So we write it as a function, review two words, which take a raw review text content, which is an HTML format, perform all this pre-processing, and give return the words. Okay, return the words, meaningful words after removing the stop word. So we can call this function for all the reviews. So in a for loop, we can call this clean train review. So we'll do these things. We'll get all the review, all the documents, all the text documents, which is cleaned. Then the next step, we'll create it. We'll apply this review towards function on entire document. So we'll get a data frame with all the documents converted, like all the pre-processing applied on the training data. So entire data set now we applied with the the pre-processing. So we have clean data is now with us. Now the next step is converting this trained data or this cleaned data, pre-processed data into a vector, because machine learning algorithms, they are expecting some vectors, numeric vectors as an input. They cannot process the text data directly. Correct. They need some numerical values, numerical representation of the text data. So that process, we have to convert the text document into a vector. So that process is normally called vectorization, text vectorization, or embedding. We are embedding the text document into some format. So here there are many approaches for text vectorization. So document vectorization. So what is the intention is that every document is represented by a set of words, a set of keywords. For example, I have 10 words, 10 documents. Each document has a set of words. So I say every document can be represented by a set of words. So for example, I will take, say, the document one, say, the boy ate apple. Document two is the boy ate mango. Document three is the man and the boy ate apple and apple. Apple was good, something. So these are the three documents. So suppose I pick the word boy, I pick some keywords, say keywords, apple, or I will write, say boy and apple and mango. So these are the four words I pick as keyword. So I can write D1 as a vector. How many times? I will first take a count vectorizer, how to vectorize the document. So count vectorizer, first approach can be a count vectorizer. So this count vectorizer say document one can be how many times the boy appears? One time. How many times man? Zero. How many times apple? One times. How many times mango? Zero. So document one can be represented as a vector 1010. Document 2 can be represented as, you can just think what is document 1, boy 1 time, man 0 time, apple 0 time, mango 1 time. So 1 1 1. D3, now you can represent D3 as boy 1 time, man 1 time, apple 2 times, mango 0 time. So this is the vector corresponding to document 3. So once we have this kind of vectors, we can input this vector into the other machine learning task. Now we can compare D1 and D2. We can check the similarity between D1 and D2 by taking the cosine similarity. How similar D1 and D2? Or what is the distance between D1 and D2? Because they are vectors, we can calculate the Euclidean distance between D1 and D2. So this is a simple approach for count vectorizer, but this count vectorizer is not good because we cannot identify the importance of a word in this corpus. Because boy is present in all the, can we identify a document D1 based on the query word B1, boy? Because boy is present in all the document. So if I search for the term boy, all the documents will be retrieved. So what could be the important words? So we will use another vectorizer that is called TF IDF. So what we use here is just term frequency or count of the word, count of the term. Instead of that, we can use a term frequency IDF frequency based weight, TF IDF. TF means term frequency, IDF means inverse document frequency. So what is TF? TF is a normalized count of a particular word in the document. For example, how many times the appears in the document, this document with respect to this document, divided by what is the maximum number of the word or total number of words in the document. So that can be the is a normalized count between one answer. So for example, boy, all words are appears one time only. So TF is number of count of WI word WI divided by now we need to normalize it. So we'll take the maximum of count of WJ in the word in the document. Then IDF indicate inverse document frequency, which is the log score of capital N divided by small n, where capital N is the number of document in which the term appears, and small n the number of times the or the sorry, capital N is the number of total number of documents, and small n is the total number of documents in which the particular document, particular word appears. So this is inverse document frequency. For example, if boy appears in all the documents, so 3 documents, 3 by 3, log 1, which is 0. So ideal value of this will be 0 because the word is not important. But man appears only in one document, so log 3 by 1, this will be a better value. So IDF score will give how important the word with respect to the corpus. And the weight of a document will be weight of not a document, weight of a word I in document J will be TF of the word in the document I, TF of the word I in document J into IDF of the word I. So weight Wij, that is weight of the I in J, document J, is defined as TF, which is term frequency of the word in the document, this value, into IDF of I. So TF of, it is Ij, which is count of the word in document J divided by maximum count of say some word K in document J. So this word will give better representation. So instead of putting just count, we can use WI1, WI2 as the count. We can even pick the top word based on this IDF value, top words which appears in this document. So that is how a TF IDF vectorizer. There may be some smoothing, like because if a word appears in all the documents, this may be 0. So a 0 into TF will may give a 0 weight. In order to avoid that, we will apply some smoothing value plus some small value 0.001. This kind of smoothing is normally applied. So that is TF-IDF. So this TF-IDF vectorization can be simply, that is a theory of the TF-IDF. We can do TF-IDF vectorization by simply using the function from scikit-learn. So we vectorize the document Here we are using n-gram range, not just single word. We'll keep all the word, all the n-grams, like between 1 and 3. So we'll take unigram, bigram, and trigram. So what is unigram? A simple word. For example, in this sentence, the boy ate apple. So unigram means the boy ate apple. So we'll count the TF-ID with respect to unigram. Then bigram means the boy ate apple. So this is bigram. And trigram means the boy ate, then boy ate apple. So we'll take chunks of the combined words with respect to unigram, bigram, and trigram. All the counts will be taken, and we'll select the maximum 5,000 word as a feature. So every document will be represented by a 5,000 words. The frequency or the TF-ID value of this 5,000 words, top 5,000 words. Okay, so this is the vectorizer object. You can see the properties of this vectorizer. We are using n-gram ranger, and maximum feature is 5,000, and we are using Unicode things. So everything is there. So we can apply this vectorizer. We can fit the vectorizer. We can learn the vectorizer from this plain word, which is the feature. And this feature can be converted into an array by two array function in this one. So you can see it have 25,000 rows and 5,000 words. So totally the training data set contain 25,000 words, 25,000 not words, 25,000 documents, and each document is represented by a 5,000 vector, 5,000 dimensional vector. So 25,000 into 5,000 dimensional matrix, the training data feature matrix. Okay, now we have the vocabulary. We can do the classification. Now we have the features. These are the features. This matrix is the feature matrix. Now we can input this feature matrix into a classifier. So for example, we can take logistic regression, random forest classifier, any classifier you can use from scikit-learn. You decide as classifier. You decide a classifier object. Dot fit function will train the model. You will get the trained data. You can make prediction on the test data. You can evaluate. You can see the score also. Okay, so this is how you can use a simple classifier, simple machine learning classifier for text document. The main part is in text pre-processing. Okay, you spend many time, a lot of time on this text cleaning as well as feature representation. You have to do some TF-ID vectorization or some other kind of vectorization to learn the vector, and then once the vector is ready, it is 2 line of code. You can just call the corresponding feature, corresponding classifier, and get the result. So you can explore this by trying with different classifiers. That is not our the focus of the discussion. So we can move to the next process. So do you have any doubt in this simple approach? A basic uh, text classification. Do you have any doubt? Is it clear? Okay, I hope it is clear. Now let's see how we can do the same thing, a text classification, a sentiment analysis kind of thing, using the latest model like LSTM kind of thing. Okay, so here what we are doing is we need to design a neural network LSTM model for doing this text classification. So the steps remains the same except the feature engineering and model selection, because the pre-processing, we may include pre-processing, and we can say pre-processing and feature selection. Largely this feature selection and pre-processing will be done by the machine itself, the neural network model itself. So we'll see how it is working. So first you are loading all the data, whatever required. So NLTK is required for some kind of works. Pandas may be required. Stop words are required. Scikit-learn, label encoder, because label need to be converted into a work vector. So that is required. Collection, counter, matrices, classification metrics. And this is the important part. You are using a deep learning model. You are creating a deep learning model. You are using Keras for doing this. So Keras have models corresponding to the deep learning models we can create using Keras. So it provides sequential models. So LSTM, RN, and everything is sequential model. And we'll use the tokenizer, pad sequences, some functions, and also the layers like dense layer, embedding layer, LSTM, sequential. All this kind of layers available in Keras. Also, we are importing to our program. We'll see what is the use of all these things step by step. And these packages are not we are not using. You can use to visualize the result, but train and split data is required. We'll see everything. So the first step, load the data. We are using Amazon Alexa review data set. So the data set is available here, Amazon Alexa, where it is. Yeah, Amazon Alexa review text. So it's a TSP file, only small 514 KB data. It may take time. So you have to first load the data. So we are using the same function PD. We are using pandas to load the data. Pandas dot read underscore CSV, the file name, which are separated by this tab. So data is now open. This variable data contain this data frame. So pandas read this CSV file as a data frame. So you can read it as a data frame. Now data contain this data frame. Now we are applying one option. Actually, this contain a review and the corresponding rating. So this data frame contain two columns. One is review column. You can see from here. df dot columns. Sorry, data dot columns. So this actually contain this number of columns: rating, date, variation, verified reviews, feedback, sentiment. Many things are there. So sorry, no. What we are doing is actually sentiment is not there in the original data set. It was not there. So what we are doing here is we'll take the rating. So this actually contains the review and the corresponding rating. So we write a function which states if the review is above 3, we'll consider this as positive review. If the rating is less than 3, we put it as negative review. Because for the data, like for a classification task, we need a labeled data. The rating cannot be predicted because we are using a classification model. We need a discrete value. So we apply discretization process here. If the rating, what we have is a rating value, which is a continuous value. So we'll use this assumption that if the rating column contains the value greater than 3, we'll return it as positive. Otherwise, we'll return negative. And this can be added as a new column sentiment. Okay, so we added a new column sentiment which says data.apply sentiments. So we can apply this on the we can apply this function on the rating, so we'll get the corresponding sentiment. So after that, we will get these are the columns: rating, date, variation, verified review, feedback, and sentiment, which is newly added, which says positive or negative. And for our purpose, we need only the review and sentiment. Other things like variation, date, feedback, nothing is important. So we can remove that columns. We'll just take verified review and the corresponding sentiment. So data dot version 1, you can just check the shape of the data also, data underscore v1 dot shape. You can see I have only two columns, that is verified review and sentiment, and it have 3150 documents. Also data underscore v1 dot, you can see some of the reviews. So the corresponding review and the sentiment will be here. Okay. So this is the data. Now you have to apply some process, some cleaning process on the data set. So what you are doing is you are refining a cleaning function that that will do some operation on the verified review. So for example, you will replace all the lowercase letters. You may replace all the special characters, spaces with null value. You can remove the stop word using English stop words. You can lemmatize and keep the lemma only lemma, like you are not keeping all entire word, all the inflections of the word. We are just keeping the lemma. So finally, this will return a df with after applying this step, like lowercase converting to lowercase, replacing the special characters, replacing the stop words, and lemmatization. So after applying this process, we'll get the corresponding df as the output. So this df will be used in the next level. You can also replace digits. So this command will replace digits. You can replace digits also. All numbers, everything is replaced. Like a similar approach we did it here for cleaning. We removed all the like this. This also you can use there. Beautiful soap. Only fixing the characters, words. So this function also you can do, or you can apply using the pandas itself. So both approaches okay, fine. The objective is clean the data by removing all those things, all the unwanted characters, and converting everything into lower stop word removal. And we are keeping lemma only. So we apply the lemmatization and we'll get the lemma. We are using stop words from English. So this will be passed as a, so we call the function by taking this as the input, and we'll retrieve the data. So after applying this function on the data underscore v1, we will get this as a cleaned data. So every review is pre-processed. We have only the lemma, a sequence of lemma is available with us. All the stop words are removed. We have only the stemma is remaining. Clear. Now we'll move to the training part or the model creation part. So before moving to that part, what we have to do here is we have the labels. So label is the sentiment part. It is 0 or 1. So normally in this case, deep learning part, the output will be a vector. Input is a vector and output is also a vector. So we need to convert this label into a vector instead of putting it as a 0 1 value. We need to convert this into a vector. So we'll apply a label encoder function. So encoding means you are converting. You are applying just a label encoding. So you can see so data underscore v1 dot head. So you are encoding the data. 1 minute. See, initially it was positive, negative, like that values over there. So we cannot take this positive, negative. We need to convert this into some label 0 1 1 0 1 2, whatever it is. So for doing that purpose, we will use label encoder, which convert the label into this text label into a numeric value, numeric label. So that is the function of label encoding. Also, you can check for null values that I missed, like whether the data set contain any null value. So I checked is null dot sum. I identified that none of the values are null because no function is required. So you can use that. So these are the reviews and corresponding sentiment is here. And after applying the label encoder, so I'm applying label encoder here, and you can see it is converted into one one zeros and ones, or I can dot sample. So both one and zeros are there. You can see it is converted into one and zeros. So that is a function of label encoder. Convert the label into a encode the label into a numeric value. Text input is converted into a numerical value. Now we need to fix the length of the sentence. We are because each review may have different length. So for this purpose, we'll tokenize and apply a padding. We fix 500 numbers. So all other things will be padded. Okay, if the text review is below 500, we'll pad with some zeros. Otherwise, we'll keep the first 500 words. So for that purpose, we'll apply the tokenizer function available on the text. We'll do the tokenizing and convert the text into a sequence of tokens, first 500 words, or we'll add padding. So up to this, we have done the pre-processing and tokenization. We are not done any feature engineering. We are not just we are keeping just 500 words from each text. 500 you can extend to any other number, but I keep 500 because my model is based on this number. So just review it. First, load the data, apply the cleaning, then remove the stopper. Every cleaning is done. Then I do the label encoding. Now the data set is ready. Then take the data set, apply the tokenizer, we got the tokens. Now we need to create the core part. We need to create a LSTM model, a deep learning model to perform this classification. So this LSTM will take, or this deep learning model will take this cleaned data, this vector as input, this text as input, the word, each document one by one it will take and learn the data. Okay, so we are giving a document as an input, not a text as, not a sentence as an input. So each document now represented by 500 words, and based on these words it will learn something, and based on this learning it will make a prediction, make it will update the parameters. So this cell discuss the creation of a model, a LSTM model. So just remember what is RNN, LSTM, everything. So it's a sequential model, one by one we are arranging the layers. So sequential model. So we can add, we first create an object of the object as a sequential model. So we can add as much as layers to this model object. Okay. So we first add an embedding layer. So we'll discuss what is embedding, because what we have is a text document. Tokenizer output is a text document. You can see what is in X, sorry, capital X. So it actually tokenize and keep the words into some index value. So instead of keeping the original value, it will provide some index, say 102, like some index value it will give. Okay, So this is the sequence X. You can check the X dot shape also. For each document, it is converted into a vector, a tokenized vector. So every document is now a vector containing the padded value, X value. Okay. So every document now converted into a padded value X. This is the value. So you are creating a LSTM model here. So the first step, so the model will so the model is like this. It have an input layer. That input layer takes the document, that is sequence of word as input. Uh, then it move to the next layer. Blank slide I require. 1 minute. See, I need an LSTM model. So the first layer is the input layer. This is the input layer. This take the text document vector. So a text is represented by a set of words. So this word W1, W2 up to W500. Every document is now represented by 500 words. So this will be the input to the input layer, which is we are not showing this input layer though. Then this layer is passed to an embedding layer. So this is an embedding layer E, which convert the word into a vector. Embedding layer means a word is now converted into a vector. So this embedded input will be given to, I'm just drawing an abstract model, an LSTM layer. So here it is LSTM. LSTM layer, and this LSTM learns something from this embedded input, and that is given to the output layer. So this is our classification model. Actually, this LSTM layer which passed to a forward network to do the classification. So this is actually the classification layer. So normally the input layer which take this text document as input, then we have the embedded layer that convert this text document, this word into an embedded vector, then converted into then LSTM layer to learn the representation. Then we have the classification and output prediction layer. So this is the steps normally we have. We have to create this model. So this model is created using this 5-6 lines. So first it is a sequential model, sequence of different layers. We can add different layers. So input layer is not specifying here. We are not explicitly specifying this is the input layer. Normally when we are designing, theoretically we'll say input layer, hidden layer and output layer, but input layer have no functionality. It will just read the input and pass to the next layer, first hidden layer. So we are not explicitly defining input layer in this model. So it is specified here what is the length of input layer here. So we have an embedding layer. We are defining an embedding layer. So every document is converted into, every word is converted into a 120 dimension. So that is specified. So input of this embedding layer, every word is now, sorry, every document is now represented by 500 words. So 500 into 120. So output will be a 120 neuron, 120 dimension. Okay. So this is the first layer, embedding layer here. So embedding layer will pass the document vector into document words into this embedding layer, and we will get a 120 dimensional embedding vector as an output of this. Embedding, what is embedding, how embedding perform, that we can discuss in the afternoon session. Here the input length dot x dot shape means this is the number of neurons in the input layer. We are not specifying a separate input layer. Here itself we are saying input underscore length equal to x dot shape of 1. That means input length of this embedding layer is x dot shape of 1. X dot shape of 1 is the number of words in that document. Okay, so we perform an embedding on this thing. Dropout we can discuss later. So we have the embedding layer, we have the embedded vector. So this layer will learn the embedding, word embedding from that document and move to the LSTM. These numbers you can fix, just randomly put some number, you can find the number. So this LSTM have 176. So this will be a sequence of layers. So we have 500 into 120, 20. So that 120, that matrix will be given to the LSTM layer. So input of the LSTM, that will take 120 dimensional vector as input and produce, there are 176 output. So this will be the output. So LSTM layer output contain 176 dimension, which is then passed to a dense layer of two output, 0 or 1. We can use 1 also, no problem, but here we are using 2 for positive class and negative class. So 2 is dense output. So dense means sorry, to insert new slide. So so what we are doing here is we have the LSTM layer nodes are there. So this is the output of LSTM. Just block represent this LSTM, which contain all the whatever required in LSTM, all the gates, all the input, everything is there. So the entire LSTM unit, not just a layer. We by LSTM layer means entire LSTM unit from input to output layer, everything is there. All the intermediate gates, input gate, output gate, forget gate, everything is there. So this will at the output layer we'll get a 177, 176 dimension output, which is connected densely to the next layer. Dense connection means every node is connected in this way. So we can say this corresponds to positive class and this corresponds to negative class. Each will have some probability value because we are using softmax at the output. We'll get a value between 0 and 1. So based on this value, we can say if this is high, we can say it's a positive class. If this is high, we can say it is negative class. We can also use a single layer at the output, single neuron at the output, which take all the input and give one value, and we can fix a threshold, say 0.5. If the value is above if the value is above 0.5, we can say it is positive. If the value in this neuron is above threshold 0.5, we can say it is positive. Otherwise, it is negative. That is also possible. That is also possible. But in this example, I use two layers at the output. So embedding layer, then LSTM layer. LSTM will give the output, which is given to the output layer, which is a dense connection of two neurons. And the activation used here is softmax. All other cases, it is the default activation function used. We are not specifying. So normally it is ReLU. So here we can, if we want, you can specify any other activation function. Why activation function is required? We need to do some non-linearity. So in order to get the non-linearity property, we will use activation function here. So this part is the model creation, embedding layer, LSTM layer, and output layer. It's a very simple model. We can add as much you want. If you want one more embedding, sorry, one more LSTM layer, you can try that. If you after LSTM layer, if you think it is better to have a flattened layer and then process something, that also possible. You can add as much as layer you want. You can design your own model by adding more layers. So a deep learning model means you are adding more layers, or you are using different activation function to do the function, do the things. So here you will get this is the model, and dropout is actually 0.4% of the nodes will be dropout. Like we'll remove some of them in order to suppose in order to avoid the over learning by the model. So there may be a chance that outliers may be learned if we are over generalization may be happen. So in order to avoid that problem, we'll apply some dropout. So in each layer, we'll remove 0.4 percentage, because based on the threshold value it learned, we can remove 0.40% of the nodes can be ignored. That is the idea of dropout. So that is there. So this is the model. So our model contain an embedding layer. So input layer, which take the document vector. Then we'll put a embedding to convert this word into a vector. Then that embedding layer will be given to a dropout layer is there. Then LSTM layer. Then the classification output layer, which contain two neurons. So that is our model. Then we'll define the compile function. We'll use a categorical cross entropy, because output is say we are expecting output. Suppose say this in this case we have two neurons, 0 and 1. One correspond to positive and the one correspond to negative. So for positive document, the output is 1. Output here is 1 and the other column is 0 for positive case, and for negative case the expected output is 0 and the next neuron will get 1. But we may get some values between like this. In positive case we may get some 0.9 here and 0.1 there. That may be possible, but this is the actual expected output. We are comparing with this output. So in order to make this comparison, we'll use a loss function called cross entropy, which compare two probability distribution. So the actual probability, the expected probability distribution is like this: 1, 0, and 0, 1. And we are comparing the actual predicted one. Say 0 means say some 0.75 or 0.19, 0.1 may be there. So we'll compare with these two things, cross entropy. We'll calculate the cross entropy, and based on this cross entropy, it will optimize the model. And we'll use an accuracy measure metric, metric accuracy to evaluate the model. So loss is categorical value, categorical cross entropy, and accuracy is this one. Suppose I print the model summary, I can see the first layer is an embedding layer which have 6,000 parameters. How? 500 into 120, so 6,000 60,000, sorry. And this dropout, there is no parameter to learn. LSTM layer 1, which have this much number of parameters, and dense 1 only this 176 into 2 plus bias, so totally 354 parameters to learn. So total, this model, this simple model, there are 2,69,442 parameters to be learned. You know what is parameters in LSTM and deep learning model. So our model have to learn this much number of parameters. Okay, so you can print the parameter summary, the model summary using this function, this model dot summary. So you will get the corresponding numbers. So here is the output. Like input layer, we are not, there is no parameters. Just read the input and pass to the next layer. So we are not counting any parameters there. Embedding layer, dropout layer, also no parameter, LSTM and dense. You can increase the complexity by adding more LSTM layers or more dense layers, whatever you want you can do. You can extend the model, you can check the accuracy, you can train the model, you can check the accuracy. Now you have the data, now you need to convert you need to train the model. So before going to the training value, you have the entire data set. You will split the data set into two parts: training and testing data. Train data split. So what you are doing is you are splitting the value into like 70% of data you will use for training and remaining 30% used for testing. So it's a random split. So a pseudo random number, seed is given as 42, any number you can give. So this function will output xtrain, ytrain, and xtest, ytest. So xtrain can be used to learn the parameters and xtest can be used to evaluate the model. Okay, so now we have the training and testing data set as ready. we can apply this model on the data set to predict, make the, we can apply the learning. So here is the training function. Here is the training. X train, Y train. The input are X train, Y train. So it's a supervised learning model. We need input. Pair. Input contain the pair, the feature vector, as well as the corresponding label. So for each training instance, we have the corresponding word vectors, the document represented in bold, and Y train, the corresponding value. And we, for the simplicity, we fix epoch as 5. 5 in the sense 5 times it will repeat on the entire data set. One epoch means it train over data all the data available in the train set. So 5 times we'll repeat to get the stable model. We'll check with the LOs, this cross entropy loss. uh, Batch size is there. You can also print verbose. I think verbose equal to 1. I can give, I think, I'm not sure. So you can train the model. You can see in each epoch how it is working. So out of 3,150 documents, I took 2,205 documents for training and remaining for testing. So only 5 epoch. You can see initially the loss was 3775. It's actually going in the wrong direction. It's learning, it's reading, and but accuracy also not changing because it's very small epoch. You need to increase the epoch to see the difference. You couldn't see much difference. It's already 87, so you couldn't see much improvement over the model. So if it is like that, you can improve the model by, like, you can change instead of say 176, you can try with some other numbers. This may be over learning. So it may take time. So you can see how it is learning. It work on every epoch. It will compare the loss, find the accuracy. You can even plot this, the loss and accuracy in each epoch. It should decrease, loss should decrease, and uh, accuracy should increase. That is what we expect. It is taking too much time. So you can see how this is increasing. It will take a batch of 32 documents. We specified 32. So as a batch mode learning, so it will take a batch of 32 documents into the primary memory. It will process and take the next data in a batch-wise mode. This is a good approach because if we have a large amount of document, a batch-wise split is good approach. It will work. It may take time. So after this process, I gave 15 instead of 15. If I give 2 or 3, you can see the difference. And after doing this training, you can evaluate the model by just calling model.evaluate on the test data. So test data is previously unseen data. You can work on the test data to make the comparison. So you can see the loss is now decreasing from 39 to, initially it was 3934, now it is 3214. Accuracy is also slightly increasing. It's not a big improvement, but you can see slightly it is increasing. This will repeat, like when it is when the training is over, you can see the difference, final difference. Even you can plot these values, like how it is increasing. You can take the history at each epoch, how it is changing, what is the average loss and average thing that you can plot uh, into history, into some kind of plot, so you can see how it is increasing or decreasing. So this is how you can do a text classification using LSTM. It will take time. Meanwhile, I can take some questions if you have some queries. It's regarding the attendance. Uh, so normally you will plot something like this. This contain the epoch, and this is the loss. So loss normally high, initially it will be high, and then it will come to a peak, and then it becomes stable. So this kind of curve you will get for loss versus epoch. Similarly, you can try epoch versus the accuracy. So it will be a reverse thing. You can see that it is getting increasing with respect to the epoch, and may get some stable ones in one position. Not exactly this way. It will be something I couldn't do. Something like that you can get. So it is again taking time. You can see the improvement. Loss is getting decreased by just changing this model into 100, LSTM into 100. The model is getting improved. Now you are getting the accuracy of 0.9293 something. So you can see the difference. So initial model have only 85% accuracy. Now it's moving to 90s. So by clearly defining a good model by trial and only no other way, we need to try with different models to find the best best model to do this function. So do you have any queries?
Participants, you can ask questions now.
Because it may take some more time to finish this running. It may depending on my 8 GB RAM. It will work better in a GPU machine. It will be better. So mine is not normal machine. So that difference is also maybe there. So what you can do is you can try with different combinations instead of this 100 or embedding layer. You can try. You can add one more LSTM layer, like you can add one more LSTM layer. So in this way, you can try your experiments using the simple tool, which this demonstration is based on Keras. There are many other packages like TensorFlow, PyTorch, and all that. Depending on your objective, you can select the package. For simply understanding the models, Keras is good one because programming wise it is very less expensive. We can simply call the package. Like creating the model is very simple. You can just add layers. Already pre-built layers are there. You can just add them to the machine. Or if you want to develop your own models, PyTorch is better because it have more flexibility. You can create your own models. So it will be like if you are creating a new mathematical model, you are defining your own layers, your own activation function. In that case, I think PyTorch will be better. TensorFlow is also good. It is very low level, so more in-depth knowledge on the deep learning working is required. So either PyTorch or Keras. For experimental purpose, Keras is fine, absolutely fine. You can use the Keras models on your works. So this is a basic text classification algorithm. Again, you can see the improvement and decrease in the loss. Loss is now decreasing to 0.45. Normally it will be 0.00. It will reach that level. And accuracy will also slightly improving. Now, initially it was 87. After 7th epoch, it is 0.94. So this is how an LSTM. So it basically it's a classification task. Only thing is that we defined a neural network model. Okay. So do you have any queries? So if no queries means we can uh, wind up the session. So let me summarize what we discussed. So we started with what is classification and specifically what is text classification, different application of text classification. So these are the general steps involved in any text processing, also in text classification. Two approaches we discussed. One is pure machine learning based, classic machine learning based. Feature engineering is important to how to extract features, how to do document vectorization manually. So TF-I, DF count vectorization, such things we discussed as part of this discussion. Then we can decide a classic machine learning model and take that vector as an input, feature a vector as an input, and do the classification. That is one approach. The second approach is based on deep neural network, where the feature engineering part is very less. We do the pre-processing, cleaning everything, and give the data into the deep learning model. So embedding layer will do that representation, feature representation automatically, extract the features and represent as a vector, and that embedding is given to the next layers, and we'll do the LSTM kind of representation learning, do the classification using output layer, and learn the model. So in that case, we need to know what are the like how many parameters are required, how many nodes are required in each layer. So that we need to define that decision. That is actually hyperparameters called. They are called hyperparameters. We can try with different numbers. A grid search approach is also better. We can systematically find number of neurons in each layer, and based on also some experience also you will get an idea like what could be the number. So based on that, you can design a model, you can train the model, you can test the model. Based on the accuracy, you can fine tune the hyperparameters and get a better model. So that is the other approach. So we used LSTM, and later you can use BERT or any other pre-trained model instead of LSTM. That is also possible. So this is the summary of what we discussed. The program is taking too much time. I don't think I can show the result, but you can see the improvement. by just simply changing 176 to 100. I just put randomly 176 and I change to 100. We are getting more good accuracy. It will take time. Only 9th epoch. 6 more epochs are there. So you can see the accuracy now it is 95. Initially it was 0.87. Also loss is decreasing. Okay.
Participants, if you have any query, you can ask now.
Okay. So thank you once again for listening. I
Okay,
hope
sir.
it was useful.
Okay, sir. Thank you so much for such a wonderful session. And our next session will start from 2 p.m. onwards and is about distributional semantics and word embedding. And the hands-on session and will be handled by Manu sir. Thank you, sir. Thank you so much.